to lecture 2. To all of you guys who came out to the work session last Saturday, thank you. I hope you had a good time. And yeah, did everybody get a chance to do the sign-in form? Alright, cool.
Okay. So yeah, kind of an overview for today's lectures. We'll be going over motor checks and just kind of going over motor control, like spin direction, power level, and lastly with encoders on just measuring how far your motor has gone and
Yeah.
rotated.
So once we get all this information, you'll have enough knowledge to actually get your rat kits moving. Alright, so to start with, we are going to look at some different types of motors just to give more context of why we're choosing the motors that we are. Okay, so the two major types of motors that you may have seen around are brushless and brushed. Brushed, I'll start with that. It is the cheaper and simpler of the two. You might know that when we pass electric current through like a lot of coils of wire, it creates a magnetic field. So how brushed motors work is we pass current through these two coils, and then we have two magnets on each side, or like north and south pole. And when we activate this electromagnet, it will turn to match up with these, and then they're called brushed motors because they have brushes. These are where the electrical components contact. So then once it's aligned here, it will switch from touching these contacts to touching these ones. So you don't need to know exactly how it works, but that's the idea, that when they switch contacts, it will switch the polarity of the electromagnet. So then it will go here, and then the polarity will switch, and then it will keep going here, and then it'll keep rotating like that. And that's the basic idea. They're really cheap and simple to make, easy to work with. But because we have the brushes here, actually touching the electrical contacts, that means it's less efficient because you lose energy due to friction, and then they're also less precise. So that's brushed motors. And brushless motors, they work on a similar principle here, where you're still working with electromagnets, but how these work, it has 3 inputs, and then they activate 2 sets of electromagnets each. So basically just taking turns activating each magnet, then that will cause the rotation. And as you might imagine, they're a lot more complex to set up and harder to work with, because with brush motors, you're good with just applying a DC voltage to wires, but with brushless, you have to have an AC signal to actually use them, and usually have a whole separate piece of hardware that controls that signal. They're hard to work with, but the upside is they're more precise and more efficient. But we don't really need too much efficiency because we're not running the motors that fast, and there won't be that much rotation that we need to measure. So that's why we are going with brush motors. Alright. Did anybody, actually first of all, alright, keep going. So these are examples of what brushed motors versus brushless motors might look like. The key difference being we have two wires going into each of these. That's just positive, negative voltage. And then these, you see brushless motors a lot on drones and high-end RC cars, just because that's where the efficiency and the actual precision matter. And you note them because these have the 3 wires. All right. Did anybody have any questions so far? All right. Cool. So yeah, these are the DC brush motors that we are going to be using in Micromouse. You may have already seen these in the kits that we passed out, but well, first of all, they're brushed, and then the main advantage, or the thing that's special about these, is they have a 30-to-1 gear ratio that's caused by this gearbox here. Does anybody know what that means? The 30-to-1 gear ratio?
For every 30 evolutions of a motor, there's 1 out evolution.
Yeah, that's perfect. Yeah, it's exactly that. So every time this motor, or in here internally, it spins 30 times, every 30 rotations of this causes 1 full rotation of the axle here. So yeah, if we spin it 30 radians per second, this would spin at 1 radian per second. Does anybody know why we might want that? Okay.
More torque.
More torque, exactly, yeah. So if we didn't have this gearbox and we just ran the motor, it would spin really fast, honestly a little too fast for our purposes, and then 2, if we just like pinch it really quick, it would immediately stop because it doesn't have that much torque. So when we have the 30-to-1 gear ratio, it would have 30 times more torque. And then moving on from that, we have the 6-volt ideal operating voltage. That, like, we're gonna be running it off battery power, so that's 7.4 volts, but it's like, we're not gonna be running it at full power, so that's why we can go above the 6-volt ideal operating voltage, and maximum current draw of 0.67 amps. And pay attention to these 2 numbers because they're gonna come up in a few slides.
And like, so the next component, like we already know like how the motors sort of work. The next part is like how do we want to control the way the motors move. So we're just gonna look at how to turn it. So the main things is we're looking at how to turn on and off the motors. We'll look at how, like which direction the motor spins because we could do clockwise or counterclockwise. And lastly, how to set the speed of the motor, how many rotations per second and all that. So as you guys have done in the last assignment, you guys have probably figured out that there is a way to toggle your pins to output in voltage to like maybe turn like an LED on. So like, surely this will work with a motor, right? Unfortunate news, this doesn't work because like a microcontroller unfortunately does not have that much voltage that it can supply, neither does it have a lot of current, and yeah. So we'll be directly powering these from the batteries themselves, and just due to like the microcontroller's limited supplies.
Yeah, the microcontroller works off 3.3 volts, so all the outputs that it can do from its GPIO pins, that's all going to be 3.3 volt levels. And then it also cannot supply nearly enough to match the maximum current draw of the motors, which is 0.67 amps. I want to say like the actual output current of the microcontroller is more like 100 milliamps, something really small.
It's
yeah.
probably in the milliamps, yeah.
Yeah.
So again, like the fact that the microcontroller outputs in milliamps compared to like nearly an amp of current that we need, you can tell why it's not that good of an idea. So part of the solution, we're using transistors. So think of it like a switch. So just consider it as a switch that's normally just on. It's normally that's just off and not connected. When you apply a voltage across like the base, or like when you apply voltage to the base, the current is allowed to flow through from the collector to the emitter. So for what we can do, yeah, like these are better suited for our smaller applications, and Micromouse, as implied in the name, is on the smaller side. So what we can do is we can just put a transistor between our battery and our ground and just kind of toggle it on and off. Since our microcontroller doesn't supply that, since our microcontroller can supply voltage, we're just going to use it as like an on and off switch instead. And we'll just have a direct connection to our batteries.
This is going to be like a microcontroller output pin. It'll be similar to how you guys activated the LED in the first assignment, where you just do the right function and then like set it to high or low. This would be a high or low. If it's high, it allows battery current to pass through and power the motor. If it's low, nothing passes through.
And since we are working with motors and they are slow to react due to just physical properties, this creates inductance. Remember working with coils in physics 1C? Well, at some point you will encounter these coils, and you'll remember that like with the change in current, it will create inductance, and the extra current that a motor may create might fry our transistors. So what we add to like not fry our equipment, we add a flyback diode, which mainly to prevent the voltage spike from the motors not stopping in time. And since diodes only allow current to flow in one direction, we just allow it to flow back to the battery, which won't fry any of our equipment. So we figured out how to turn on and off the motors. The next part would just be how to figure out what directions the motors turn in.
Were there any questions about the previous slide so far? Alright, oh, yeah.
So does the transistor act as like a type of motor controller?
The transistor just acts like a switch.
Yeah,
That,
and then,
like it just basically, it functions as like a switch that's normally off, and the microcontroller tells it to turn on. The microcontroller basically, whenever it like sends a signal over, it just completes the circuit. If that makes sense.
yeah, but your question about motor controllers, we're gonna get into the next slide. So yeah, alright, take the next slide.
Yeah. Okay.
Yeah, so, the most common type of basic motor controller is called an H-bridge. So let's first of all, just like take a look at this schematic real quick. These are the flatback diodes that we talked about on one of the previous slides, and then Q1, Q2, Q3, and Q4 are all transistors. And then we have our DC motor here, positive voltage, and then ground. So, if you ever worked with like a DC motor before, you'll know that like when you pass in a voltage to its two terminals, it'll spin one way, and then if you reverse the voltage, it'll spin the other way. So like, if I apply positive here and negative here, let's just say it'll turn clockwise, positive here and negative here, it'll turn counterclockwise. So we can take advantage of this fact using this schematic here, and then let's just say we turn on transistors Q1 and Q4 and turn off Q2 and Q3. What would happen? Current would flow this way, so from positive to negative here, and then let's just call it our counterclockwise rotation. And then if we turn off Q1 and Q4, but instead turn on Q2 and Q3, what we get now is current flows the other way. So then that will cause it to rotate counterclockwise instead. And then you might notice that something bad could happen with this setup, and that would be if you turn on all four of these transistors at the same time, and that would result in a short circuit where positive voltage is connected directly to ground, and you will fry your H-bridge and maybe some other components. So don't
Please
do
don't
that,
do
please. Were there any questions on how that worked?
Could I type that down?
Sure, which part?
Oh, could I? Let me just type it.
Okay. We're also going to post these lecture slides on our Google Drive folder if you ever need to look back. And also post a recording of this.
So it's only the motor direction that can be controlled by this, or also the motors?
This setup specifically controls motor direction. We will talk about how to control motor speed in a later part of this lecture.
Yeah, so the whole point of the H-bridge circuit is to control when to turn on and off the motors, and also what direction. So yeah, that was the previous slide had like the general like circuit design, but then this is the actual like IC that we're gonna be using. Like IC meaning integrated chip, just like the actual like chip thing that we're gonna be putting on our boards. Yeah, so if we look, see if this laser pointer works. Ooh, can you guys see this all right? All right, cool. So yeah, we have 4 inputs on this. We have 1, 2, 3, 4, and that would be connected to the pins, output pins of our microcontroller. These are connected directly to the transistors. So, like on the previous slide, we would turn on Q1 and Q4. Same idea here. Oh wait, one thing I forgot to mention here. Let me go back to this slide. So we're never gonna turn on like Q1 and Q4. Q4 are always gonna be either both on or both off. So what we do in the dual H bridge is we just combine those inputs. So like passing a high voltage to input 1 would turn on Q1 and Q4. So this H bridge controls 2 motors. So it has 2 inputs for each motor, and then 2 outputs just connect to the positive and negative leads of each motor. So that's why there's 2 of each. So that was kind of jumbled explanation. You feel free to ask questions after. But yeah, so we have inputs and outputs here. Oh, one last thing. There is enable pins that are meant for each motor. This just means like when we pass this a high voltage, then we are able to turn on the motor. And if these are never passed a high voltage or just like left unconnected, then we're not going to be able to do anything with this. This is just like more of a safety feature. so we don't turn on the motors when we don't want them to be on.
So like basically the H bridges, the two H bridges are built into the IC.
Yeah. So like
Okay.
this circuit, the whole thing here, like, well, first of all,
And-
take this out and connect it to the two output channels. We're gonna be like shoving in two of these circuits inside this one IC.
Yeah, and the other thing is like we kind of take advantage on like
Oh.
we kind of take advantage of just how like we have sets of transistors turning on at the same time, so that's like kind of in part of how it's compacted into the H bridge on the next slide.
That.
And here's a sample schematic of
Oh.
it.
Sorry. Yeah.
Wait, but if you compress the transistor to a smaller size, how's it still able to like sustain the current like without burning itself? Like
Oh, sorry. By compress.
By
like-
compress, I just meant like since
No.
like they both take the same signal and they both either they're both on, they're both off. I meant they just combine into like.
Yeah.
that's
So
what's needed.
let's just say input 1 is connected to both Q1 and Q4. So that's why we only need 2 sets of inputs for each motor. Yeah.
wait, I was talking about the physical side. So when you have an individual transistor, it's like this big, right?
Mm-hmm.
But then how do you put 8 of them into like something that's similar size but still have it be able to do the same function without
Well,
losing?
there are smaller transistors out there.
Yeah. Well, I mean, like transistors can be any size, and they are each rated for like specific voltages, like voltage ranges. You can check the data sheet to see like how low or how big of a voltage it can handle, but transistors can be pretty small but still handle a big voltage load. Yeah. Okay.
What does GMB stand for?
Ground.
Okay.
Oh yeah. So yeah, we covered enable pins, inputs, outputs, and ground. VSS, that will be the battery voltage that's gonna be flowing through the motors, and I believe that's
That's
all.
all.
Yeah. All right. So this is the schematic that you're gonna be doing in assignment 2B. We're working with Autodesk Equal, but let's just look at how we've set it up. So we have, first of all, we got enable pins here and here, passing a high voltage that no matter what, the H bridge is always enabled. And then after that, actually, yeah, after that we have our battery voltage here going straight into the VS and VSS. We have 2 decoupling capacitors, similar to how we put them on the linear regulator last lecture. These will just, anytime there's like a bump in voltage, a voltage spike, it will absorb the excess current, and anytime there's a voltage drop, it will release some of that absorbed current. So that's just to keep the battery voltage here as stable as possible. And then we can also see the output pins here. These are connected to the 2 prongs of each motor, and then inputs here are connected directly to our microcontroller. And then this is what our actual physical H bridges might look like. This is the one that we are going to be using on our rack kits. It will have like a nice slot right here on the PCB. The reason we use this and not like the one that we soldered on is because in case you guys accidentally fry them by turning on all inputs at the same time, it's easy to just take it out and replace it. We don't want you to do that, of course, but like that's just a precaution. And then this is like an example of an H bridge breakout board that I've seen on Amazon a lot. If you're ever doing like RC car stuff, this is one you might consider buying. It's just like it has slots with inputs, outputs, voltage regulator, all that jazz. And yeah, those are H bridges. And that's how you control the direction that the motor spins. Were there any questions about that? Right.
And then so the last bit is just kind of more on motor speed. So as you guys have been questioning a lot, it's like, yeah, so right now it seems like it's either completely on or completely off. Yeah, with the current way that we've set up and that we've introduced this setup, yeah, it's just the only settings for now. But there is a way to adjust like motor speed, so we could go at like half the speed or 3/4 of full speed and all that. So think about it like on and off being like black paint and white paint. So we could just mix on and off together to create some middle ground, like averaged out voltage. So yeah, and due to the fact that motors are physical and have inertia, they respond slowly to rapid voltage changes. Yes.
We also have used like a variable resistor, or is that not?
A variable resistor, considering how much like load, and it's like one thing is like we want to automatically adjust the motor speed and not have to like manually adjust it. If you have like a variable resistor, so like this is how we can more smartly implement it. So yeah, you could just mix on and off states to form like some middle ground, like for example mixing black and white paint to form gray. And what we can do, and this is commonly called in PWM, pulse width modulation, and as you can see, you can see it's just like you could like mix half and half for 50% duty cycle, 75% on, and 25% off for 75% duty cycle. You're just kind of balancing out the ratio between the amount of time it's on and the amount of time it's off to control how much you're getting. And duty cycle is the percent of time that your motor's in the on state, and frequency is the number of cycles per second. Yes.
Sorry.
Pulse width modulation.
I guess we didn't include that on the slides, huh? Oops. Okay. We'll add it to the slides after
We'll add it
this.
to the slides. Yeah.
Okay.
But, yeah. So, and you can see here's just a visualization. Like if you had a 100% duty cycle, it would have just been like a solid line across the top. But you can see now we just kind of lowered it based off of how long it's on versus how long it's off. And
Yes, this would be like half speed, like 75% speed, and 25% speed.
And yeah, so you might be wondering, okay, what's the smarter way to implement it as to answer the previous question? We're kind of using this based off of the timers on our microcontrollers. So we're kind of looking at the clock speed that the microcontroller, like basically how like it fast it processes its info, and then how fast the H bridge can handle as well. And then we could just kind of use these two numbers to determine the counter of 3200 clock cycles. And yeah, the pulse value is the amount of clock cycles to stay on per period. And like, since we have 32,000 in a 75% duty cycle, that means 2,400 clock cycles on and 800 off to create like 75% of the speed. And yeah, like this, you can apply similar math and just kind of adjust it to find like a speed that's like, oh, it's just, you just do the math and figure out like how long does that have to stay on for 50% speed and all that.
In the software, you don't actually have to calculate this. Like you can just say like, oh, I want a 75% duty cycle, and then it will generate this PWM signal for you.
This is just kind of going through the math of it.
Yeah.
Do you have a question?
Yeah. Wait, so then you can control the ratio between on and off, but like how long is the on? Like can you control that? Like
How
is it on for 1 second, off for
It's kind of
1
more like
second,
in
or-
terms of clock cycles. Which
Yeah.
is
So
like,
clock cycles, I think that would correspond to the microcontroller clock speed. 16 megahertz. That means it. One clock cycle would be like 16 megahertz. Hertz is like cycles per second. So like 16 million.
it's just like it'll be fractions of seconds, to be honest.
Yeah.
Like
thousands, like tens of thousands of seconds.
it's like, cause when you think about it, like you might be thinking like if we're doing this at a rate of like 1 cycle per second, you might think it's really slow, but in reality, it's actually performed really quickly. So it's a smooth transition of like creating like a steady voltage, even though you're turning it between on and off. Does that make sense? Alright.
Yeah.
And yeah, like in our microcontrollers, like we'll be working with 3200 clock cycles, but like yeah, it's a little bit of fraction. and stuff. Yeah, so we are done figuring out the motor speed, but there's still one thing. We actually have no way to track how far we've gone, how much we've gone, how fast we're going, and this is where we introduce encoders.
So yeah, like right now we can turn the motors on, they turn and stuff, but it's like driving blind. Like you don't actually have any feedback or like know how far you've actually gone. So ideally we want to be able to measure how much our wheel has rotated, because that's the easiest way to tell how far we've gone, like how much we've turned. So the idea is encoders, there's multiple ways to do it. The general, most common way is to like attach something to the back of the motor. It's like every time it spins, like that thing spins. There's two ways you can do that, either with magnetic or optical encoders. Optical ones, it's like if you have just like a wheel here and then a sensor here that can detect the like beeps on and off of the light when this spins. That will be a pretty accurate representation of how much it is spinning. But then the encoders that we are going to use are called magnetic encoders. So these sensors, these are Hall effect sensors that can detect whether it's in front of a north pole, or like the north pole of a magnet or the south pole of a magnet. So yeah, when we spin this magnetic disc, it will read like, oh, north, south, and then as we'll show on the next slide, that will give us an accurate representation of how much we've rotated. Alright, are there any questions so far? Yeah.
On the slide, there's like 20 magnets on the disc. About like how many magnets would there be on like the encoders we're using?
Yeah, I'll get into that right now. So, these are the magnetic encoders that we're using. If you took a look at all the components in your kit, you may have seen that we have a motor connected to, and on the back of it we have this and a magnetic wheel spinning. So this is a 6-pole magnetic disc. So you have 3 north poles and 3 south poles. And then, in addition to that, the sensors that we have are 2 Hall effect sensors. These are the ones that can detect whether we're in front of a north pole or south pole. And detects the presence of magnetic field. Hall effect, if you're curious, you'll learn more about it in your physics classes, but it just creates a voltage difference from detecting its current and magnetic field around it. And then getting into how we're actually measuring stuff. So let's just say this is our encoder, and we have our magnet here that's spinning. We know each of these magnetic poles are 60 degrees apart, because 360 degrees divided by 6 for each one, 60 degrees. And the Hall effect sensors are 90 degrees apart. So what we can do, or that would be 30 degrees per encoder count. So let's actually see let's take a look at what the microcontroller would see when we're reading these inputs. So right now, it's at 0 degrees of the spin. Sensor 1 detects north. Sensor 2 is in between these, so it doesn't register as reading anything. But then when we turn a little bit, now we turn 30 degrees. Sensor 2 will detect the south pole. Sensor 1 won't detect anything. Let's go again. Sensor 1 gets south, 2 nothing, 1 nothing, 2 north. And then after that, after we've done 120 degrees, we're back to north. So you just see like this is the general flow of what the microcontroller sees. And then if we want to look at counterclockwise motion, we can do the same thing. There, and we go to 30 degrees, 60 degrees, 90 degrees, 120 degrees. And you'll notice that these are in opposite of each other. So here we go, north, south, south, north, north. And then the same thing here, but reverse, north, north, south, south, north. So that's just how the microcontroller actually sees and detects like, oh, this is counterclockwise motion versus counterclockwise motion. And also it increments in counts of 30 degrees. So every time the motor spins 30 degrees, we go from one state to another. You might think that, actually, I'll get into that later. Spin direction, yeah, that's what I was talking about here. Okay. So you might think that like the 30 degrees per rotation count like is not accurate at all, but remember that we have a 30-to-1 gear ratio. So the 30 degrees counts like the rotation of the actual motor, not before it goes into the 30-to-1 gear ratio. So if we do some math to see how accurate these encoders will be for actually measuring our, like how far we've gone, we can go here. So it has 360 degrees per rotation, 30 degrees per count. That leads to 12 counts per full rotation, full motor rotation. That's just like the individual motor before the gearbox. And then feed that into the 30-to-1 gearbox. We get 360 counts in the software for every one wheel rotation. And then that's basically like if we attach a wheel, we can detect like 1 degree differences between when we turn it. And then wheel dimension, it's about like 3.2 centimeters. That's a 10 centimeter circumference. So then if we translate the rotational motion into linear motion, that will give us 36 encoder counts per centimeter. So we can count in like 1/36 of a centimeter, which is pretty accurate. The wheels will skid like a little bit, which would make this count a little bit off, but for our purposes, this is pretty good. Any questions? Alright, cool. So yeah, and then using our encoders with the microcontroller, we talked a lot about how like, oh, this is what the microcontroller sees. We did that on purpose because we're not actually gonna be reading the direct like north-south inputs, because that's a lot of effort to set up. It is possible, but since people use encoders with microcontrollers so often, the creators, STM32, the creators of these microcontrollers, they actually implemented a thing called encoder mode. So the outputs from these two Hall effect sensors get the things that read like the north and south. They get passed into two microcontroller pins, which we configure with timer channels. And then we can set in STM32 Cube IDE, we can set these pins to encoder mode, which will output just like an integer number for like how many encoder counts has passed.
And just as like a short recap, so again, it still centralizes around the microcontroller. It sends a signal to the H bridge, to like which like controls how fast the speed, direction, and just how in general the motor turns. And like the amount the motor turns is passed on to the encoders, which is again the amount the motor turns. It's directly counted in the encoder that the microcontroller processes and presents as an integer number to us. So yeah, it has an output to the motors and it has an input returning from the encoders.
Yeah, and then in the next lecture we're going to talk about actually using this feedback that we get, like how much rotation in our programs, like our like to get precise movement. Yeah. So.
Is it viable to like instead of using encoders, like instead do like some sort of like integration to determine like the distance of how it has traveled? Or?
So you have the right idea, but the one problem with that is we don't actually set like we can't just tell the motor spin like at this like spin like 0.5 meters per second. We give it like the duty cycle in voltages, but like it also very much depends on like the level of voltage that your battery has, because like if it's a little bit drained, then the motors will spin more slowly. So there's no way to actually guarantee that like what we see in software is how much the motor is actually turning without getting some sort of feedback back into the microcontroller.
And like feedbacks, actually, we will talk more about it in the next lecture in our more precise controls. But like for now, we have it set up. It'll be useful, and
So yeah, we're gonna be quickly showing you kind of similar to how we did in the last lecture, what the end goal is for doing this. I'm going to open STM32 Cube IDE right now.
don't be intimidated by the rest of the stuff here. I know it's still a lot, but don't worry about it. Like, you guys will get here, promise. And right now we're just trying to just do a little bit of demonstration, and we'll actually show you a really helpful tool present in STM32 Cube IDE called Live Expressions, which during debug mode actually shows you like what your current value of a variable looks like. Like say if you have an integer that's a counter, it tells you how many counts is stored up and all that.
Okay, so yeah, right now I commented out like a bunch of this code. All it does right now is set a variable called left counts to what our left encoder is reading, and a variable called right counts to what our right encoder is reading. And then these are global variables that I defined up here. And because they're global variables, we can actually see like in real time what these variables are showing right now. So if we just, alright. So then I set it up like left counts and right counts here. We're viewing the live value. So then when I spin one of these motors by hand, I'm gonna spin the right motor backwards. You'll
and
see,
you can see like this quantity, it's like it's changed to like negative 194.
Yeah, okay. That's the left motor actually.
Well, it's like either way, like it's still noticeable on like how the how like the values change and like how sensitive it actually is, because we barely moved this other motor and it's still like saying that, oh, you've also turned this in the other direction.
I'm gonna spin this left motor 180 degrees and let's see how many counts it will count. So yeah, like we said, it's about give or take 1 degree per encoder count. Yeah, and then I'll spin it back, and then we can do the left one. So yeah, these live expressions are a really helpful tool that you'll learn how to use in the next assignment to measure the variables and like actually see what the microcontroller is seeing. And then I can also show you the function that you guys are going to be setting up in your code. Oh yeah, so you're going to be able to just like set the left motor and right motor duty cycles. So we don't actually have to do any of the math like how many clock cycles. We just say like, oh, I want a 50% duty cycle. So let's just say I'll set the right motor to 50%, 40%, and left motor to 60%. And then it should, we're uploading the code right now. Yeah. Going. Just a show of hands. How far are you guys in assignment 1? I guess raise your hand if you haven't started at all. Okay, that's fine. That's fine. You guys have time.
It's like,
and then how about like you started the assignment, like you got some soldering in, you're like going through it right now. Like in between the assignment. Fucking how many of you are finished?
Which part?
Everything I guess? Alright, well,
it's okay. We have work sessions next week, and we still have a little bit of time between our next work session and the assignment deadline, so like, you guys have a little bit of time to figure it out.
yeah, so that code uploaded, I unplugged it so that it's gonna complain. But yeah, so then when I turn it on, the motors are indeed spinning. And then
They are going at different speeds, though, so it's going to go in a circle.
we're going in a circle. So yeah, that's just the demo that we wanted to do. I'll show you guys what the goal is for this next assignment that we're going to be releasing this week.
Yeah, any questions? Any questions for this lecture that we haven't answered yet?
Alright.
Alright, cool. So we do have a little bit of end of lecture logistics. Yeah, so one thing, we'll be trying to make, I know like we've said in like the first assignment, we want you guys to have a group chat, but we also thought it would be nice if like us two and your team had a group chat together as well. It'll make a lot of logistics in winter like a lot easier on us, and like it'll be easier for us to just kind of be like, hey, just kind of check in once in a while, you know?
Yeah, so what we're gonna ask you guys to do right now, if any of you have your like Discord on your phone, just like open Discord on whatever you have. If you don't have Discord on your laptop right now, that's fine. Just do it after this. But open Discord, open IEEE Discord channel. I want you guys to all, I know we've been kind of spamming you guys about this, but we really need to make sure that you guys have it. You're in add roles, and then you have clicked the Micromouse icon here. So then after that, you will see like, oh, I have the Micromouse role here, and then you have access to our Micromouse announcements, links, questions, and general chat.
Hold on. Yeah? You got a question? Okay.
Okay, yeah, so make sure you have this role, make sure you can actually see this because we're not sending out any more emails, just we're doing everything on here, it's a lot easier. And then after that, we want you guys to all add us on Discord right now. So if you are
Okay, wait, raise the hand.
Wait, hold on. If your Discord said you're not open.
What?
Oh.
damn Megan, okay.
Sorry, let me go fix that real quick, but like, yeah, it's, okay, you guys are all in the IEEE server, right? I don't have to just kind of tell you guys where to find the invite link.
Okay. Well, while she
Hold
does
on.
that, what you do, if you're on this page and wanted to add us just really quickly, just right click on one of us here. It will show you a bunch of stuff. Let's just do it real quick. I'm gonna go friend an officer that I apparently don't have on my friends list right now. Tyler. I right click. I go to add friend. That's all. And then another way to do it, you could just like go to profile, and then this would be a send friend request. But yeah, that's just the two housekeeping things that we wanted to get out of the way right now.
Okay, and also I fixed my friend perm, so you guys should be able to have me now.
Yeah,
Sorry about
so everyone, if you could go add me and Megan on Discord, that'll just make things a lot easier. Thanks guys, and then I'll give you guys like another minute to do that. Bruh, what do you mean you had your friends off? Yeah, it's fine. It's fine. Back into the camera view.
that. So,
Alright, yeah, well we'll just assume that everybody did that, and if you didn't, please do it after.
or at least have one person in your team run us. So
Preferably everybody.
Preferably everyone, that makes our job a lot easier, but.
Okay, yeah, next one.
Yeah, we have
Oh.
made a little bit of amendments to 1B.
Oh yeah, so we realized we did not actually show you guys what it's supposed to look like at the end. So this is for assignment 1B, you're creating the linear voltage regulator circuit. So this is what you should have at the end. We did edit the assignment, we just add like one extra paragraph, it shouldn't take too long. And then also one last thing, these VCCs, these are like shorthand for implicit connections, meaning like anytime there's a wire labeled or connected to VCC, that just means these wires have like an invisible wire connecting them. So all the grounds are connected and all the VCCs are connected, and this is a really useful feature because we don't have to like have tons of wires going across the page. So another thing, it's like the same idea as these implicit connections. We add a label here, like we label this wire as 3.3 volts because that's the output of this voltage regulator. And then this wire,
And
if we have any other wire that has this same label, 3.3 volts, then that will have an implicit connection, like an invisible wire connecting them.
So like the pins that are labeled ground, the ends are that are labeled ground are actually like ground, or we just use them to sort of say they're connected.
Well, ideally, if you do have a circuit, this will be your ground.
Okay.
Yeah.
I
I mean, it's just, in general, just more like these tags, they do just connect your stuff together. But like, generally these will be connected to your power sources and these to your grounds.
Yeah, if you're talking about like actual ground, the actual ground in this case will be whatever your voltage is being powered by, aka your battery. So this is real ground, and then everything is connected to that.
Okay.
So yeah, so that's just that. If you've already done assignment 1B, please just like check out the last page. We just added this to make sure that like it was clear what we wanted you guys to do, and then side.
Yeah, just a few reminders. Like, we have the soldering workshop that we've been telling you guys about during our work session. This Thursday, hosted by Workshops Leads. It'll be on the first floor of Bolter Makerspace, starting at 6:30. There will also be a PCB design workshop that will be coming up next Tuesday from 6:30, and it's on Zoom. We'll be having our third lecture 2 weeks later from today, so you guys get a little break next week.
Instead of going to lecture next week, attend this because this will give you a lot more experience in like you guys have experience like doing the schematics in Eagle, but now this will give you more experience working with like the actual board layout part. Yeah, so please go to the soldering workshop and PCB design workshops. Those will be very helpful. Soldering workshop, that will give you like practice with SMD soldering. So like that's the harder type of soldering where it's not through hole. It does not go through the board. It's just like a flat thing that goes onto the board and like sits there. Yeah.
Yes.
We have a CS midterm on next Tuesday at 6.
That's so this day?
Yeah.
Alright.
Okay,
We might move the workshop.
We will communicate with the workshop leads and we'll update you if that date changes.
Okay, that's a Smallberg midterm, right? Dang, I forgot about that one. Okay. Well, okay, if nothing else, if we don't change the date, then it will be recorded on Zoom. Yeah. Anybody else?
Are we gonna have a lecture the next Tuesday as well?
No, our fellow lecture is like November 1st.
I think.
Yeah.
Yeah, for any of you guys taking CS31, don't worry. We will be trying our best to avoid lectures on your midterms.
Alright, we're not done yet, by the way.
And then
yeah.
the assignment is due next week.
Due next week.
We're trying to have a work session Wednesday.
Yeah, we're trying to have a work session October 26th. So that's for you guys to get started on assignment 2A and 2B, which we'll talk about in a minute. But
or
also
finish up 1A and 1B.
Yeah. Okay. It'll be like same format as last work session where like there's no goals, like we're not gonna teach about anything new. It's just for you guys to have a dedicated time where we're gonna be there to work on the assignments. Alright, next slide. Speaking of the new assignments, assignment 2A and 2B, same format as last time. Oh, one thing I forgot to mention, how we format the assignments is there's going to be an A and B part for them. The A part is like working with the actual rack kits. That will be a group assignment. You guys should be doing all of that together, hopefully. And you got only one person per team needs to submit whatever we tell you to submit for this assignment. But for assignment 1B and 2B this time around, that will be the individual assignments working with the actual Autodesk Eagle. We want you guys to all get experience working with Eagle. So we ask that you guys all submit your own stuff for assignment 2B. Just like work on it. You can still work on it together, but the idea is you all get experience doing this work.
It will make winter a lot easier for you guys.
Yeah, so assignment 2A is SMD soldering, like I was mentioning earlier. You're just gonna install the motors, get the motor rotation working like I showed in the demo, and also measuring the rotation using lab expressions. Assignment 2B will be more Autodesk Eagle. We're going to be talking about the H-bridge schematic that we showed earlier. You're going to be creating that in Autodesk Eagle. And then also the connectors where the encoders are. And that will be due November 4th. Yeah.
And yeah, thank you guys for coming.
All right,
Wait, do you want to share the poll results?
Yeah, we're going to share the poll results because for all of these, well, at least last week and this week, there was a correct answer. So let's see what you guys thought.
Let's see how you guys did on this vibe check. And we promise, we do try to want to have a little fun in here. So here is the fun part.
Okay. So let's see. 61.3% of you, 61.3% of you guys said Miriam's the simp and Eli's the gamer, but 38.7% said Eli's the simp and Miriam's the gamer. Megan, you live with Miriam. You're around her a lot. What do you think?
Well, as Miriam's roommate, I have to say, unfortunately, a majority of you have the wrong answer.
Yeah, Miriam is the gamer and Eli is the simp. Let's go.
Let's go.
Alright. Well, yeah. That is all we got for you guys today.
Thank you for coming.
Yeah. We'll be dropping assignment 2A and 2B tonight, so just whenever you want, just start looking at that.